it jumps out so naturally out of what you guys are doing right now. It would be criminal for us not to look at it. And it's just a really, really beautiful confluence of all these concepts that you have spent the last month and a half developing. Okay, that's how long we've been thinking about like this kind of thing and derivatives. Okay. So what you've noticed is that there are functions with odd and even symmetry, right? So I just call them odd and even functions, right? When we're thinking at the moment, right, all that we've been dealing with is polynomials, okay? So it's just polynomials of odd and even powers, okay? So for instance, this guy here, right, is your quintessential even function, okay? And we already know that on the basis of this guy, what's our derivative? You should just be able to read it off, 2x, very good, okay? Now, x squared is an even function. And its derivative, f dash, is odd. You've looked at other ones, right? For example, let's have a new function. By the way, after f for function, g for gunction, is the next most popular one. Now, if we think about the next polynomial up, the next power of x cubed, having an odd power, it's always fun. You only just got it? Is that what you know?
It's not as bad as the intersquare.
Yeah, that's true. That's pretty bad. The derivative of g dash, is of course, you can read it off, 3x squared. Very good. G is odd. I might even put these on. Color. G is odd. And then G dash is even, which is exactly the reverse of what we noticed up here. And I could multiply examples. Right? Like x to the power of 100 is going to be odd or even. It's an even function. In fact, x to the 100, it just looks like a really, really steep version of x squared. It's x squared that's gone on the paleo diet, basically. Okay, and that's right. It's yeah. So rather than looking like this, right? X to the 100 would look something more like this. Basically, okay. So it's even. Its derivative is going to be odd. So what's going on here, right? Like just before, when we saw this, like these power businesses, we thought there's got to be a pattern here I can take advantage of, right? And there was, and we worked out, we derived it, okay? There must be a pattern here. How would we identify it, okay? Well, I'm going to consider, here's where you can follow along with me. I'm going to consider if, let's do odd first. If f is odd, okay? Once we go through this proof, you'll see it's almost identical if we were to reverse the situation and think about if f were even. We only really need to do it once to demonstrate what's going on. Okay? Now, if f is odd, then by definition, what do we know about f? What can we say about f?
It has even odd.
Think in terms of our notation here, right? F of minus x is equal to minus f of x. That's the definition of an odd function, right? And then we think about the symmetry that comes out of that, okay? Now, what I want is to therefore prove, what I'm required to prove is I'm looking for its derivative being odd. The derivative, sorry, this is odd. I want the derivative to be even, right? So I want f dash x, I want that to be even, so therefore what can I say about f dash?
It's equal to
f dash of negative x, right? And minus x. There we go. That should be true. That should be true. Okay? Now, we have done a lot of first principles, right? So we know what f dash x is. Limit h approaches 0, da 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 da. So we know what this looks like. So let's have a go at this guy. Let's tackle this guy, right? So I'm going to go right hand side equals f dash of negative x. What is this thing? Okay? Well, it's the limit as h approaches 0 of what? Well, every time I normally just picture first principles in your head, everywhere I see an x, I'm going to put a minus x in its place. Does that make sense? That's what I'm going to do. Okay. So I've got my limit, right? On the top here, I would usually have f of x plus h. but I'm thinking about minus x. So this will be minus x plus h. See what I'm doing? I'm just evaluating it at a different spot. Minus, now normally I would put f of x on here, but instead, I'm going to put f of minus x. Question?
Why isn't h minus?
Okay, so,
It's minus h.
Oh, right.
Flop up until the little
no. She's right. It usually is x plus h, right? But think about what this means, right? If, for instance, I wanted to get the derivative at, I don't know, say a certain point, 5, okay? All that means is the limit as h approaches 0 of, okay? Now, what's going to be on the top? It's going to be 5 plus a little bit, right? Minus 5, right? Like that, okay? So 5 is the place I'm looking at, right? That's the particular spot where I want the derivative, okay? The particular spot here that I want the derivative is at minus x. I guess this would be thinking on like the opposite side, right? You've got it over here, and now I'm looking on the opposite side of the axis. So I still want to go there plus a little bit, right? Plus a little bit. That's all I'm doing, okay? And you can see it here as well. Like if this was minus x, then this would be minus x plus a little bit, plus h. Does that make sense? Just be on this side. Yeah, exactly right. Okay, so it would be like over here and over here. There'd be minus x and then it'd be minus x plus h, and then I'd get my etc.
If you did put the h as a minus, would anything go wrong?
Oh, that is a great question, and we're going to answer it in about 2.5 minutes. Okay, so let's get there. Now remember how we started this. We said by definition that f is odd, so this is true, right? So therefore, in here, and let's just be super careful with our brackets, right? I want to take advantage of this fact. So I'm going to rewrite this guy as f of minus x minus h. Why am I doing that? It's because it allows me to use this property. That whole thing in there has to be negative, right? So I pop a minus sign right there, okay? And that whole thing in there is negative, okay? All right, now, I've already got this in the form that I want. I recognize that. This is going to be equal to this, right? You following with me? That's all divided by h. Okay, now I'm going to execute the odd part of the function. So this is the limit as h approaches 0 of, by definition, I should be able to put a minus sign at the front there. Minus f of x minus h. You see what I did there? Okay. Odd functions can do this. That minus sign can hop out the front precisely because it's odd. Not for any other reason. In exactly the same way, this guy can come out the front and it clashes with this double negative, right? So it'll be plus f of x. You agree with that? Okay, now, I like things to be neat. I don't like the negative out the front and a plus in the middle, so I'm just going to rewrite that like so. And then I get this. Now you stare at this long and hard. This looks strange. This is simplified for sure, right? I've gotten rid of a lot of like random minus signs out there, okay? But it's not like anything that I'm super familiar with, okay? Except it is. It's just in different clothes. Do you remember? I gave you this definition of first principles, right? I also gave you that that slightly different one. The limit as c approaches x of f of c minus f of x on c minus x. I think that way, or the other way around. Anyway, whatever. That different form of first principles is still doing the same thing. Now, what would this be? What would it look like? Okay. Here is regular first principles up the top. Okay, that's regular first principles. This is x plus h, right? So I have this run here. Okay, that's why it's on the denominator. Okay, and then remind me again, what have I got here? What have I got here?
The rise.
I've got the rise here, right? There's f of x plus h on the top, f of x on the bottom, and then this distance here is you take the difference, hence the minus. Okay. So what would this look like? X plus h is x plus a little bit. X minus h is x minus a little bit. I've gone the other way, okay? So instead of having x and x plus h here, I've got x and x minus h is behind me. Does that make sense? X plus h goes a little that way, x minus h goes a little that way. tell me, what's this distance here? It's still h, isn't it? It's just h the other way. Okay, it's still h. Okay? Now, it's just a distance. It's just a distance. Run is just a distance. Okay? Now, if that's x minus h and that's x, what's this y coordinate over here? This is f of x. And what's this y coordinate over here? F of x minus h. So, what is this distance? Isn't it this?
Oh, it is.
It's just that, right? Now, think about this. Remember, and this is the beauty of it, right? We're thinking about, we said it 1, 2, 3, 4 times, the tangent, not the secant. So, h going that way, h going this way, I don't care. H is going to be nothing once I've evaluated it, right? It's going to be a tangent, not a secant. So therefore these two pictures, did you notice? They're the same picture, right? This is still f dash, right? It's still the gradient at that point because h is going to vanish off to 0. What was the right-hand side again? It was this. That's the right-hand side. F dash minus x is equal to f dash. It's even. The derivative from first principles of an odd function must be an even function.
Oh my god.
Okay. And of course, you could rehearse this all over again. You just have minus signs in slightly different spots. If instead you started with an even function, down here you would end up with an odd function when you do the derivative. Okay. I think that's extraordinary.